what I wanted to talk to you about is, oh, how do I put people? Yeah, I want to see some faces. Oh, there's no. What I wanted to talk to you about, in fact, is essentially my research on my climate research of the past about close to 20 years, which has focused on the Sahel region since my postdoc onwards. And I want to talk to you quite a bit about, are the slides moving? I hope so.
Yes, yes, it's good.
Yeah, so I want to tell you the climate change story about the Sahel, and so give you a long-term view perspective, if you wish, on this region that is very much in the news. Because in fact, piecing together bits and pieces over 20 years, it's actually come together quite nicely, this story, the climate change story in the Sahel. And so we've gone all the way to attributing, in fact, the late 20th century droughts that made this region conspicuous in the 70s and 80s. And so I'll talk quite a bit about the climate science, but also give some, present some discussion that's not really my research, but other research that considers environmental change in the region and its relation to adaptation. And so, yeah, really the idea is to, and also tie things together in such a way that to try and make the argument for climate change, science and policy actually being a way out to envision a different future for this region. Okay, so if you've heard about the Sahel, most likely you've heard about the Sahel for one of these reasons that are depicted here with these figures. For example, at the bottom here on the right, especially in Europe, the Sahel is often invoked because of migration out of the Sahel and towards Europe. And so this is one of the dominant concerns, together with the one related to terrorism in the Sahel and the political instability. And then there's one related type of crisis that is food security that actually, that I depicted here with this map from the famine early warning systems. And this actually, the system of monitoring food security dates back to the droughts of the 70s and 80s. And then oftentimes when environmental change is discussed, it's more in terms of desertification rather than regreening. So this is kind of like the short-term view, if you wish, to presently what we most often encounter when we hear discussions of the Sahel. But in fact, from a climate perspective, the Sahel is interesting because of this, the decline that led to the map from the fourth assessment report of the IPCC, the observational chapter that shows, oops, can you hear fine? Because my internet, yeah, I'll keep talking. Okay, so what's depicted here is the linear trend in precipitation globally. And so the Sahel stands out. It's this region here of Northern Africa. It stands out because of this large decline in precipitation, large in both spatially and quantitatively in magnitude. And I would argue that it stands out, even though there's an interesting trend in the opposite direction over Southeastern South America, but that's a whole other issue. So this is the climatic change that I'll be discussing, this decline in precipitation over the 20th century taken as a whole. So this is what it looks like in space. And in time, it looks like this. This is actually a time series derived from meteorological observations over the Western Sahel, let's say from Chad westward. And put together, it's an analysis from a regional institution called AgriMet. And so here, this time series here, it starts in 1950 and goes to, I put a bar here because this is 2005, so it's the endpoint of the map that I just showed you. But so essentially what you see, this is the decline that is depicted, that was depicted especially in the map I just showed you. So an epoch of abundant rains. So these are anomalies in precipitation with respect to the long-term mean. So green means abundant precipitation, and brown means deficient precipitation. And so you can distinguish these three epochs, if you wish, of abundant precipitation in the 50s and 60s, then the decline and the persistence of drought in the 70s and 80s, and now what some people refer to as a partial recovery of rains that is actually characterized by a lot of year-to-year variability. So this is, on the face of it, what climate variability, climate change looked like in the Sahel in the 20th century. Now, I don't know, I almost wanted to run a poll here to get raise your hands if mostly what you heard about the possible causes of this decline in precipitation and the persistence of drought in the 70s and 80s. If most of what you heard actually is the second hypothesis that I describe here at the bottom. So something connecting land degradation, bearing of soils, and drought in a positive biogeophysical feedback. And as opposed to what I found, this actually on the right here, this picture is, this image is a cover of this magazine, The Ecologist, from October 1973, which quite remarkably actually put forth an alternative explanation that actually connected pollution with the acid rain crisis in Northern Europe with droughts in the Sahel. And so I'm going to ruin the surprise for you. I'm going to go in this direction, actually, so show you that there's actually elements of this pollution to drought story in the record and in the way we've come to understand this climatic change. So I'll talk mostly about the physics of this past climatic change, and then a little bit about adaptation, and so what we've learned from societal response to drought and to this discourse of desertification. So the causes of Sahel drought. Well, actually, let me go back for a second and give you a little bit more of a characterization of what the Sahel is and where it is. So in terms of vegetation cover, it is the southern edge of the Sahara Desert. And so it's these ecotones here of shrubland, grassland, cropland in yellow to green to red. So the southern margin of the desert, and the contours here are climatological precipitation. And the first line is 400 millimeters per year. And then it increases. So precipitation increases going south. And it is also, in climatological terms, the Sahel is the northern edge of the West African monsoon. And so here, this is the seasonal variation in precipitation in shades of green, and near surface winds in the arrows. And so what you see, let me run it again, is this meridional migration of precipitation. And so there's one rainy season which is during the hot season. And so the Sahel is wet for about 3-4 months, let's say from June to September. And winds reverse following the rains. And so there are southwesterly monsoonal winds during the rainy season. So let me try to stop it at its peak, which is in August. So that's the climate. So this is really, precipitation is really what defines the climate in this tropical region. Oops. Okay, so the climate science story, I'm going to step through this so there are 4 steps to it, to understanding what caused the droughts of the 70s and 80s. And I'll rely mostly on my work, but obviously there's a lot more work out there. I just wanted to give you kind of my own stepping stones of how I came to understand this climatic change in the Sahel. So the first step is actually demonstrating that it was the oceans that caused the droughts and not land use change. And this, in the early 2000s, the way that we would go about doing this is that our climate models were really models of the atmosphere. And so the dynamical atmosphere and boundary conditions included observed sea surface temperatures. And so with this setup, you could actually attribute, if you looked at regional variations in for example, precipitation, as is the case here for the Sahel, and you looked for a comparison between observations and simulations, then places where you could reproduce the evolution of precipitation or climate were places that you could say were where the oceanic influence was dominant. And so this was precisely the setup used here, an ensemble of models simulations in the blue. So the red is the same trace that I showed you, the 20th century evolution of Sahel rainfall in observations. And this is reproduced by this model where the only tie to observations is the boundary conditions in sea surface temperatures. And so those evolved globally as observed and leads to this simulation of the ups and downs of Sahel rainfall. And if you look a little more closely at which regions of the ocean correlate with the variations in Sahel rainfall, then there, in terms of the long term, really the shift from wet to dry, it's the regions around Africa. But let me step back for a second. So here, these blue here are negative correlations. So precipitation is above average when sea surface temperature is below average. And so there's, you can see that most of the blue is in the tropics. So when the tropics are cool, there's more precipitation. When the tropical oceans are warm, there's drought. And so the Pacific part is understood to be related to the El Niño Southern Oscillation, but that plays a role on interannual timescales. On interdecadal timescales, it's really the oceans around Africa. And what was most conspicuous in this analysis was the warming of the equatorial Indian Ocean. And so the association between the warming of the ocean, of the tropical ocean, and drought. And perhaps in retrospect, what's also conspicuous is the lack of a warming signal in the North Atlantic. Okay, so that's where we were in 2003. So this relationship between observed sea surface temperatures and Sahel precipitation. The second step came a little later, and this actually uses CMIP-3 models, so models, coupled ocean atmosphere models from the coupled model intercomparison project phase 3, which were the simulations used in the 4th assessment report of the IPCC. I know it gets confusing at some points, but so what did these models show? So in this case now, the setup is coupled models, ocean and atmosphere interacting dynamically, and the boundary forcings are, in the case of historical simulations of the 20th century, anything and everything that could have affected the climate system during the 20th. That includes what are typically described as anthropogenic forcings, such as emissions of aerosols and greenhouse gases, but also possibly land use change and all kinds of pollution. And natural forcings would be variations in top of the atmosphere insolation and volcanic eruptions. So what's remarkable about these simulations here, and now this is a slew of models from CMIP-3 in the vertical here, is that if we take a very simple measure of reproducing Sahel droughts, that is precipitation at the end of the 20th century larger or smaller than a pre-industrial control simulation where all the external forcings are held fixed, then what's remarkable is that really no model produces a significant increase in precipitation under these conditions for a Sahelian average. And quite a number of models actually reproduce significant reduction in precipitation. So those would be the models that exceed this shading, which is a measure of significance, if you wish. And so I kind of shaded the right-hand side out, but the conclusion here was that it was clear there was something that really made climate models converge at the end of the 20th century, but diverge, but the same models diverge in their projections of future. And so the way Michela Biasutti and I interpreted this was to say, well, what really makes the coherence at the end of the 20th century is the aerosol forcing. And in contrast, when you're only dealing with, or when you're dealing with the dominance of greenhouse gases in the future, then models are very uncertain in the way they respond in terms of tropical precipitation and Sahel precipitation. And this actually, there's quite a lot of literature beyond that ties this role of aerosols at the end of the 20th century to Sahel drought. And in fact, around the same time that I published the work on the oceanic influence, Rothstein and Lohmann here in the middle panel had shown in idealized simulations with and without aerosol forcing, that aerosol forcing, which came, I guess around that same time, became known as global dimming, by cooling the northern hemisphere, imposed a sea surface temperature gradient in the Atlantic that was conducive to drought in the Sahel. And so this so the spatial imprint of aerosols is known because aerosols last in the atmosphere only 1 to 2 weeks. So they are rained out somewhat efficiently, and so they really impose a spatial footprint in that they are closest to where they were emitted. So at the end of the during the second half of the 20th century, most of the emissions were in the northern hemisphere, and so the northern hemisphere didn't warm up as much as the rest of the world as a consequence. That's what became known as global dimming. And so that's the middle panel here. The left panel is actually comes from the first modeling study that made this relationship, that made this connection and demonstrated this relationship between sea surface temperatures, a certain pattern of sea surface temperatures globally, and Sahel droughts. This is work from the UK Met Office. And so the pattern that this sort of idealized pattern they imposed to reproduce droughts was one where, again, you had warmer southern oceans, kind of the same pattern I showed you, warmer South Atlantic than North, some warming in the equatorial Pacific and the equatorial Indian Ocean. And coming closer to present, there's also this, I have to show you this intriguing plot here because it's really where a lot of research is now, and is that this is also work from the UK Met Office, from Booth et al, that actually goes as far as to claim that all of the variation in North Atlantic sea surface temperatures is driven by aerosols in the 20th century. It's quite provocative topic still, and yeah, perhaps that Alexei will discuss this when Alexei, I don't know, when you give your presentation, it'll be interesting to go into it. So there's these different factions, if you wish, of explaining the current modern North Atlantic sea surface temperature records. Is it internal variability, such as what is usually called Atlantic meridional overturning circulation or Atlantic multidecadal oscillation or variation, or is there a dominant influence of sulfate aerosols? Okay, so then going in the direction of trying to converge things and give us a physical explanation of what explains drought and recovery or variation more generally, is this third short article. And so this is where we really put together and came up with a synthetic idea, like synthetic interpretation that really tries to explain variability and change in the simplest way possible. And so the scatter plot here shows the correlation of Sahel rainfall on the x-axis, so below average or above average, and an index of sea surface temperature that is the difference between the North Atlantic and the global tropics. And so the correlation is quite high, 0.7. And so, and also in the color of the dots here, I'm depicting the wet phase in blue. And so Sahel rainfall above, mostly above average, because the North Atlantic is warmer than the global tropics. Then the red phase, with the persistence of drought, is in red. And again, Sahel rainfall is below average because the North Atlantic is cooler than the global tropics. And then now we're in this variable epoch, and we're going back and forth between wet and dry conditions. So to sketch very briefly the dynamics of things, and how do these two factors, so these two indices of sea surface temperature, North Atlantic and global tropics, how do they explain these variations? So here I'm using this cartoon that was used by Zhang, in fact, to make the usual case that is made to explain Sahel droughts, which is that it's the interhemispheric gradient in sea surface temperature in the Atlantic that counts, that matters, and that the intertropical convergence zone follows the warmest sea surface temperatures. So if the gradient is in this direction, cold North Atlantic, warm South Atlantic, the ITCZ shifts south, and so does rainfall in the Sahel. So there's less precipitation all across the Sahel by continuity, if you wish. So this is the standard picture. I want to actually change it a little bit and put it in context of climate change. And it's actually an explanation that is essentially the same explanation was invoked also possibly to explain variations in hurricane frequency or in the North Atlantic. And so the idea here is that, in fact, one element is the warming of the global tropical oceans. And what this does to the global tropical circulation, the global tropical overturning circulation, is that it is the warmest sea surface temperatures that actually determine, set the conditions for this overturning. And so the warmest sea surface temperatures dictate where it is going to convect, where there's going to be deep convection and precipitation, and what that condition is that needs to be met globally. So if the oceans, when the oceans warm, then this condition is this threshold is raised, and there's what David Neeling calls an upped ante for convection. And so convection, deep convection and overturning becomes more difficult in places that do not warm at the same rate. So that's the global tropical oceans warming component, and then what I attributed to the Indian Ocean at the beginning of this discussion. And so the second element is, well, can this threshold be met? Can this threshold for convection be met? And locally, this threshold can be met, I argue, if the ocean also, if the local ocean warms, and when the local ocean warms, what it does is that it actually it supplies the moisture that is needed to meet that higher threshold. And so, yeah, so these two elements are what needs to be taken into account, and what goes into this NARI index, North Atlantic Relative Index, that correlates so well with Sahel rainfall. And so historically, what has happened here? So here the bars are the same time series of Sahel rainfall I showed you earlier. And these two lines in blue and red represent respectively the North Atlantic and the global tropics. And so this is just the full time series. It's smoothed with a 21-year running mean, but it's the full time series with the trend, with all the trends included. As you see, there's a warming trend everywhere by the end of this, in the second half of this period. And so the wet phase can be explained by the fact that the North Atlantic was warmer than the global tropics in the 50s and 60s. And so that meant that the North Atlantic was able to supply sufficient moisture to produce convection. In contrast, then, as you can see, in the late 60s into the 70s and 80s, then the warming of the global tropical oceans emerged at the same time that the North Atlantic went into a cooling phase. And so warmer global tropical oceans than North Atlantic means translates into drying. And now we're in this phase where we actually have warming everywhere. And so there's opposition of these two influences of warming. And that could explain that the large year-to-year variation. Okay, so let me stop for a second here. So now what I'm gonna explain, so this, then how does this tie in with these external influences of aerosols and greenhouse gases? Well, so the idea here is that, well, the warming due to greenhouse gases is pretty clear in this warming trend in the red curve, especially that, I mean, it starts earlier in the red curve in the global tropical oceans. And then the role of the aerosols, if you follow to some extent, well, without going all the way to saying it's all the variation in the blue curve is aerosols, at least the part that says cooling of the North Atlantic, especially manifest in the 70s and 80s, is associated with emissions of sulfate aerosols, is consistent with this idea that this is when aerosol concentrations peaked, especially around the North Atlantic basin in North America and Europe, because this is really post World War II and into the 70s and 80s, before legislation was enacted to curb the emissions of sulfate aerosols, that this cooling associated with sulfate aerosols would have manifest. And so I come to the final steps then, that is using the next generation of global coupled ocean atmosphere models, the CMIP5 generation used for the 5th assessment report of the IPCC. Then what I'm showing you here are time series of Sahel rainfall again, and the red is observations. This is over the entire 20th century. So the red is the observations again, and so you can see again the clear above average precipitation, the abundance of rainfall in the 50s and 60s, then the precipitous decline marked by severe drought in 72, 73, and then 82, 83, 84, and then some sort of a recovery towards the end of the century. And so I would argue that the yellow line, which is a multi-model mean of all the models, around 30 models, I think we used in this analysis, actually follows this, is able to simulate the decline and then the recovery. And in fact, perhaps we could discuss, in fact, what's interesting here is that the decline in these simulations, where what's really manifest here is the response to external forcing, starts even earlier than in observations. And so now the question becomes what's going on in the 50s and 60s, because models forced with these with emissions actually say that it should have dried earlier, starting from after World War II, from the 50s on to the 80s, and then with a partial recovery at the end. And the green lines are single models. So this is one way to do attribution in a very simple way. If you wish, I'm not really doing the whole fingerprinting, but what I'm proposing to you is more of the physical argument of tying the oceanic influences. And so I started with tying the oceans to drought, and now I'm removing myself a step from oceans and saying anthropogenic emissions of aerosols and greenhouse gases affected the surface temperature of the oceans in such a way that's engendered Sahel drought. And so this is a summary of about 15 years of research, going from the first demonstration, really full-fledged demonstration of the historical evolution of Sahel rainfall, when an atmospheric model is forced with observed sea surface temperatures, to then this demonstration that anthropogenic forcings have contributed to this evolution. And so I like to highlight this because we oftentimes we say bad things about climate models, but here it's pretty clear that there has been a remarkable development in these last 20 years in what these models are capable simulating and so allowing us to better understand variations in regional climates also. Okay, so now perhaps the more fun part of the talk, in the sense that I wanted to show just showing you very qualitatively some elements of adaptation. And so the point I made up until now is that there has been climate change in the Sahel, and now I want to go back to understand how, what adaptation has occurred to drought, and can this be a template for adaptation in the future. And so again, along the lines of discussing the fact that climate change is in the present, this is actually taken from work by anthropologists who worked in this region of northern Burkina Faso. And in interviewing farmers, they got this description of variation, the change in the character of precipitation. And so lower annual rainfall, the recurrence of big rains and dry spells, violent thunderstorms, and then changes in the phasing of the rainy season with an effect on crop varieties and so on the agriculture in the region. And this is corroborated, in fact, by quantitative work analyzing time series from Burkina Faso. So this is at national scale. What's depicted here is again this same variation, evolution of the Sahelian evolution of rainfall. So with wet 50s and 60s and dry 70s and 80s. But what's done here that's remarkable is that there's more of really, again, going into the details of the character of rain. And so what's shown here in the solid lines are elements of this character of precipitation that are consistent, and that those are total annual rainfall, number of rainy days, and the cessation of the growing period. They kind of go hand in hand through these epochs. And the two elements that behave somewhat differently are the onset of the rainy season, which really remarkably a positive trend, in a delay, consistent delay in the onset of the season. And then intensity of daily rainfall, which changes somewhat differently. And so qualitatively, what can be said at the end of this time series is that this partial recovery of the rains is due in equal terms to changes in the frequency, so in the number of rainy days, but perhaps more interestingly, in an increase in the intensity of rains, which is understood to be a possible hallmark of how the hydrological cycle would change under warming. So how have farmers adapted? And again, it's qualitative. So here we are again in the Sahel. I wanted to show you some pictures that I had the good fortune of taking myself because of trips to the region for various reasons, including teaching and participating in the Climate Outlook Forum. And so I just want to, I'm showing you the two ends from my own experience. And so this was in 2011. We were at a conference on the regreening of the Sahel in Dakar, and then we went out. We did a little bit of development tourism, as they call it, and we ended up in this plateau inland from Dakar. And it was remarkable because turned around and you see in the landscape, you see there's clear signs of erosion here. And then just as clear signs of these stone contours that are put in place. And they are put in place perpendicular to the direction of erosion so as to reduce that erosion from runoff and precipitation. And here at the other end of the Sahel in northern Ethiopia, this is actually a little village that is also known for a beautiful, one of these beautiful churches excavated in the rock. But in terms of global environmental change, it's a well-known experiment, if you wish, with methods, with different techniques of environmental management. And so in this landscape, when I was there, what was pointed out to me was that this big tree in the middle here is the only one that's actually a tree that predates the droughts of the 70s and 80s. all the rest, all the vegetation that you see around it is more recent. And so here again in the landscape, there's all kinds of signs of what's called, if you wish, in general terms, soil and water conservation. You see here is along the slopes. There are sequences of check dams to again reduce the runoff and allow for the water to pool behind and then seep into the aquifer. And then here in the top, it's very small, but there are lines of rows of ditches, I guess. There were about, say, a meter long and half a meter wide and about half a meter thick. And the idea there too was to collect the rain and then allow it to seep into the aquifer. And then finally, at the bottom here is a well, and the most remarkable thing about this well is that you see that there's a pump here, but there was no need to pump. The water was just trickling out naturally. So the water level has risen. So the water table has basically risen to the surface because of all these interventions. This in a region that in the 80s, the government had plans to abandon and just move people out of, and because of the droughts and the fact that really agriculture had become apparently impossible. So there's more, and this is more evidence of these kinds of works and interventions, changes in the management of the landscape. This is from an article in the New York Times that shows these two aerial pictures here, the same landscape here. It's really the village scale, and very few dots on the left, lots of dots on the right, and these are trees. And typically in this, Niger is well known for this, for the way that agroforestry has really taken a hold in the wake of the droughts of the 80s. And so that these are trees that oftentimes this is referred to as farmer managed natural regeneration. So there are trees that farmers knowingly allow to grow on their fields because they know that they bring nutrients or both for the chemistry of the soil, but also possibly for consumption by humans and also animals. And so this is along the same lines. It's back in Burkina Faso. It's a village scale. So here you see here the scale is 1 kilometer. And so it's the change between 68, 84 and 2002 in really the land cover, the landscape. And what's to note here is in this pinkish hue is degraded land. And then the hatchings are soil water conservation treatments. So you can see the evolution of those. Well, from 68 to 84, you see, for example, if you focus here on the right-hand side, you look at the change here in both the extent of the degraded land, and then the extent of soil and water conservation treatment that was put in place that actually reduced the extent of degradation in the end. And so those are the lessons that we've learned then. But the reason that they may be interesting is that because these practices are really go in the direction of reducing the impacts of those extreme events in precipitation or soil erosion or land degradation. And so if that's what awaits in when the hydrological cycle becomes stronger and spins up with warming, then those could be techniques that would be relevant to adapting and to reducing the impact of these extreme events. And for those of you who've heard about the Great Green Wall, I think there's a lot of discussion around that and whether, in fact, these are the kinds of projects and interventions and actions that should be taken to strengthen the resilience through environmental management. Okay, so here's my conclusions then. So what I really wanted to show you in terms of the physical climate change is that climate change has already occurred in the Sahel. We can have a discussion about whether future climate change will look like the past or not. I would argue not, because as I showed you, a big component of past climate change was aerosols, and we're not in that situation anymore. The future climate change will be dominated by greenhouse gases. And secondly, so there are lessons to be learned from adaptation to drought, as I just showed you, even though vulnerability is a broader discussion that requires understanding the broader socioeconomic conditions along the lines of what I discussed in Strasbourg. And then finally, I mean, we are climate scientists looking at understanding physical climate change. We don't do much of this, but it's really clear that in terms of the long-term view on this region, the other facet of climate change that could really potentially be very beneficial for this region is the mitigation side of things, and the fact that this is a region that needs energy to develop, and it has very little energy supply right now. And so it's really a candidate, I would argue, for transitioning to a low or no carbon future. And so what, as a naive climate scientist, I would ask, what would be the global policy instruments that should or could be put in place to ensure that this transition is at least tried here. Yeah, so now I kind of, in a way, I'm kind of contradicting myself. And so I showed you what climate change means for the Sahel, but by no means does that mean that I think that climate change drives everything in the Sahel. The conflicts and the crises that I mentioned at the beginning go beyond climate in my view. But a long-term view that takes climate change with all the benefits that it can accrue in this region would be beneficial, because there's clear pathways for adaptation and mitigation in this region that would enable sustainable development. Thank you.
Okay, thank you very much, Allessandra. I'm sure there are questions. So if you have questions to Allessandra, you can either raise your hand, type it in the chat, or also raise your question in the question and answer too. And I think Alexei was the first to raise his hands, and we have several participants, so it'll be a lively discussion. Alexei.
Very nice, Alessandra. So I have actually two questions. And one question related to physical mechanisms. So in your correlation maps, you showed connecting precipitation over the Sahel to sea surface temperatures. The Indian Ocean appears to be a major player in this. Can you explain the dynamics? Because I would think the West African monsoon is largely controlled what's happening in the Atlantic, not the Indian Ocean. So that's my first question. And the second question is related to the future. At least some of the models show actually precipitation increase with global warming over the Sahel. How robust is this conclusion?
Yes, thank you, Alexei. Yes, so the Indian Ocean, if you wish, it's I kind of went very quickly on that, but it's an El Nino analog argument, if you wish, that it doesn't really matter where the warming happens, but what the warming in what you could consider could characterize as a remote ocean from the Sahel. So not the ocean that supplies the moisture to the monsoon, but other oceans, so the Indian and the Pacific. The warming there, what it does is that it, to the extent that it triggers convection, then it results in warming of the upper troposphere, and so stabilizes that way. I don't know if you're familiar with that. So that's the argument. So it's the warming of the ocean is connected to the upper troposphere and to vertical stability through convection. And then regardless of where that happens, because the tropical atmosphere just adjusts to that warming. The warming is then propagated across the tropics by waves in the upper atmosphere, in the upper troposphere. And so everything warms.
Mm-hmm.
And so then you have a warmer upper troposphere that's set by wherever the warming and the convection has occurred. And so then everywhere else has to deal with that up the ante, with that higher threshold for convection.
Okay, thanks.
Yeah, you're welcome. And so that's the argument of how, if you wish, the Indian Ocean on these multi-decadal timescales, on the trend timescale, and but also the Pacific and the ENSO influence on the region works. Then the second one, yeah, the future. Yeah, that's a good question. Maybe we should. I'm sure we should discuss this in greater depth, because right now I'm actually having the, yeah, I definitely think that the future is different from the past because of this role that aerosols played in the past. And these were aerosols around the North Atlantic. And so then we largely did away with them. So that's why the North Atlantic is also warming now, in parts at least. But then what's interesting to me that I haven't really wrapped my head around yet is, okay, you have a trend, but you can also have these multi-decadal variations. And so what's the relative amplitude of the two? Yeah, because as you can see, it's, yeah, but it's not just the Atlantic, it's in this relative sense also.
But
So I'd be, so the Sahel getting wetter is consistent with the general sense that it's when things get warmer, yeah, where it rains more.
Mm-hmm.
But whether
Okay.
it's a trend or to what extent it's modulated is an open question, I think.
Mm-hmm.
Thank you.
Okay, so we have a question by Chinaza Ikelu. You should now be able to talk, Chinaza. Hello, do you hear me?
Yes, I can hear you.
Okay, please ask your question.
Yeah, my question goes first. Thank you for the presentation, Alexandra. Please, could you go back to the last slide or last few slides? Hello, can you hear me?
Yes, we hear you. Allessandra is exchanging.
Yes, which one?
Yes, I wanted to get your email address.
Ah, okay.
And
so this one.
It's up now. Okay, do you have a question to the talk?
yes, I have a question. Could you go back to the previous slide?
The conclusions.
No, the last one. Go back further. Go back one more. One more.
This one.
Yes, this one. Yeah, so from this you talked about local knowledge. Okay, yes. So I just wanted to confirm my understanding of climate adaptation. You talked about local knowledge. I mean, this is where, how do I say, what's the word again? I've forgotten the word. I mean, when you talk about local knowledge, you talk about, for instance, you have different adaptation strategies for different countries. You know, so
yeah, there was one about farmer managed.
Yes. So the word I'm looking for is indigenous knowledge. Yes.
Yeah.
So I wanted to confirm my understanding of indigenous knowledge. I mean, it works well in adapting to climate change, and then the soil and water conservation. So I mean, it's a very good presentation. I'm glad that I had attended the webinar. Yeah, so it will help me further in my study. Yeah. So I just wanted to
definitely. I called it local knowledge, but other people also call it indigenous knowledge. So it's all these techniques that were improved in the advent of the drought. You know, they were known, and then they were worked on. For the people that stayed back and decided that they were not just going to move to the cities because of the droughts, they responded to droughts by innovating around these techniques. And so I showed you
Yeah.
just a few pictures. There's a lot more about, maybe you've seen these, what I think it comes from Burkina Faso, zais. So these pits that people make in their fields so that they can collect both the manure, the fertilizer, and the water around plants. And so everything that makes more efficient use of water, of rain in the end, right? If it's rain-fed agriculture. I mean, certainly there will be limits to that, but some of it really seems to gel with this idea that that climate change could bring about more extreme, more intense rains. And so one trick is to really try and deploy all kinds of techniques possible to catch that water when it falls, and then and reduce the runoff in contrast. Yeah.
Thank you very much for the presentation.
Thank you.
Okay, thank you, Chinaza. Maybe I have a question, Allessandra. How does droughts, etc., also relate to population growth in the Sahel? I mean, I believe that there's population growth there as well, and so is there something like do you relate the amount of rain falling also to if you compare how much rainfall increased now, is that outpaced by the population growth, for example?
Okay. Well, I can it's an interesting question. Certainly population, this is one of the regions of the world where there's a lot of population growth, but there's also a lot of migration to cities. And so I think you'd be surprised if you looked at population maps or demographics to, for example, realize that in Senegal, the one example I know best, 50% of the population is actually urban. Mm-hmm. And so there are studies there's one big study that was done in I think I want to say 98 by the OECD that kind of gave a long-term perspective on the Sahel and actually discussed this in more economic terms, so there are all kinds of trends and not necessarily, very static, but a lot of dynamics and a lot of change and
mm-hmm.
And but okay. Populations, the other thing I want to say about populations is that, you know what the population of Mali is, for example?
No, I don't.
Yeah, so, a population of Senegal, Mali, Burkina Faso is between 15 and 20 million. Then, of course, then you have a giant like Nigeria, which is more like, I'm not sure, maybe close to 200. Mm-hmm. But many of these countries, actually, if you think in comparison to our population densities, they're still small. And then if they concentrate more and more into cities, I think climate change could bring about interesting, questions there too, because how do you ensure that actually cities are well adapted? For example, there's a very interesting work about the fact that Dakar and its suburbs now flood every year because the rains have recovered. And because of a lot of the building went on during the drought years. And so people built in low-lying places where they shouldn't have, and now that it's raining more again, these places get flooded. Mm-hmm. So, okay,
so
it's very varied, I guess. There are these interesting studies and by, I guess, mostly French, and OECD, they kind of also give a perspective of the variation across the Sahel. And
mm-hmm. So for building, it's also important to know that there will be more rain as there will be more floods. Okay.
Right.
James Clark.
Yeah, thanks, Allessandra, for an interesting talk. I guess for the non-climatologist, I tend to think of rainfall over a big continent like this as being driven by the strength of the monsoonal flow, the temperature differential between land surface and ocean. It seemed like you were focusing really on how this aerosol cooling in the North Atlantic has shifted the location of the ITCZ. It seems like, and I guess going back to the earlier question about the importance of the Indian Ocean, that the eastern side of South Africa has been in long-term drought as well. And I guess I can imagine that ocean cooling would potentially decrease that differential between sea surface and land surface, but at the same time, the land surface is also warming. So I wondered if you could say a little bit more about the role of the strength of the monsoon, and also have you also seen the position of the ITCZ sort of recover and shift back to the north as the aerosol load in the atmosphere has declined?
Okay, yeah, maybe I can go back and try to clarify a couple of things. One is that actually my argument, so I think this, trying to connect a lot of the variability, especially the multidecadal variability, was explained by way of this meridional gradient in sea surface temperatures. But the point I actually want to make is that it's not that gradient so much, and but it's really this vertical stability, which it's kind of hard to explain in a way, but to have convection and deep convection and precipitation, this is like water in a pot boiling, right? You heat it from below, you heat it from the surface, and so one element is heating from the surface. Can you stir the atmosphere into this overturning?
So this refers to the stability over the ocean surface.
Also
correct?
Over land, everywhere.
Okay.
You could think that you need the heating, and perhaps what you were referring to as the fact that land. So in fact, what you were referring to as the fact that land warms up more than ocean, then in terms of temperature, land would be favored because it's warmer, and so you can produce this overturning, right?
Yes, that was my question. Yeah.
Yeah, but in fact, the other element that's becoming clear and is being elucidated in quite a bit of more theoretical work, for example, by Michael Byrne, O'Gorman, and others, is that it's not just the energy picture is not just temperature, but it's also humidity. And so when you throw in humidity, you kind of complicate things again, because then you have more humidity over the ocean. And so how do you transport that humidity over land? It's those gradients that matter more. It's not just a temperature gradient, but it's a temperature and humidity, which in climate science speak we call moist static energy. And so it's that, and then, but not just at the surface, also aloft. Because if you warm aloft, then you stifle this overturning.
Okay. Yeah. Thank you.
So, yeah. No, thank you. Yeah.
Okay. Next is Julie Desais from the audience. Julie, please.
Yes. Hi. Thanks for taking my question. A nice, very interesting talk, Alessandra. I'm a climate modeler, but I won't get into the physical points or details here. I'd like to have your view on the communication of uncertainties, both in the climate model outputs, but mostly in our understanding of the physical mechanisms you've been exposing today. Of course, everything is not yet fully understood. There are things that we understand more than others, and there are still pending questions. But yet, what you're advocating for is to actually engage into transitions, into mitigation, into adaptation. And this requires a long time scale of preparation and of logistical decisions. And how do you keep convincing your collaborators, yet explaining all the uncertainties about climate change, both in the past and in the future?
That's a good question, Julie. I hope we have a chance to discuss in person also, no?
Yeah.
Yeah, uncertainty. Yeah. I actually try to not discuss uncertainty, and my prerogative has been more to try and provide a physical argument to understand how things work, even though I realize that sometimes that borders on the, really the very disciplinary, it's not easy, very easy things to explain in a way always, but yeah, the argument is more physical, if you wish. The uncertainty, it's true that there's uncertainties about projections, and also one way perhaps to try and go around it and build an argument is also to engage with what's happening on the ground. And so that's why I think all these studies that actually show what trends and variations are, how they, what has been observed in recent years is interesting. But ultimately, they're political decisions. And I mean, we're all confronted with these same decisions. How do we make these decisions in our democracies or everywhere? So how do we, again, my naive climate scientist stand would be, we need to engage with civil society and discuss, because it's not up to us to decide anything, but if we can provide as complete a picture as we can based on all that we understand, then it should be people who decide of their future. It's not on me to say Senegal should develop following a low carbon, no carbon, transition. It's the people in Senegal should be put in the position to decide. And I think the same applies to France, right? Are we debating these issues in the context of the presidential campaign or not? It's
yeah, that's true. Thank you very much. I'd be glad to discuss this further with you in person.
Thank you.
Thank you.
Okay,
Thank you.
Venkatramani. Sorry,
Hi, Ali.
Balaji.
Yes, Balaji.
Balaji, sorry. That's much easier.
Yeah.
Sorry. Stop struggling with Venkatramani and just say Balaji. Yeah. So yeah, two questions. Thanks a lot, Ali. And like Julie, I would like to say it's a pity we haven't met in person these last few months. I hope we get a chance. So I have one question which is more on the climate modeling side, and one which is following up on the more on what to do, the policy front. So it seems from what you said that this is being driven by a temperature contrast between the North Atlantic and Indian Oceans. So in your earlier results, in your attribution studies, you showed that if the North Atlantic is staying relatively cool and the Indian Ocean is warming, then you reduce the gradient across Africa, and that seems to weaken the Sahel rainfall. And now we are, the aerosol forcing aspect, as you said, is gone. But I wonder if so now we expect that there will be warming both in the Atlantic and the Indian Ocean, but I don't know if the models are robustly saying what the difference in the rate of warming of these two will be. And that without that robust gradient of temperature, it's hard to say. And I think I've seen some of these results, at least from CMIP5. Some models seem to say that if you look at Sahel rainfall in the 21st century using some scenarios, some models show weakening, some models show strengthening, and I don't know what it is like in CMIP6. I did not follow. But I wonder if this relative warming of Atlantic and Indian Oceans is robust in any models. Have you looked at it? It's perhaps related to Alexei's question earlier as well.
Yeah, exactly.
Yeah.
But yeah, so in fact, when we extend this analysis, like the last analysis I showed you, the one based on the paper with Alexei Kaplan, to the future, it turns out that in the future, what dominates is really just the warming. If you just do the same, so with Alexei, what we did is, I'm going to go into some horrible math climate jargon, but if you do as silly as it sounds, if you do a PCA, principal component analysis of these two indices, North Atlantic and global tropics, then you get that one of the PCs is the difference and the other one is the sum, roughly.
Sure.
Yeah, so the difference is what I emphasized.
Yeah.
And explains the past.
Yeah.
But the future, to the extent that most models actually seem to be tending towards wetting the Sahel in the future,
I see.
then that just goes with the warming.
I see.
So in a way, if both warm, the difference cancels out and the sum takes over.
But I seem to remember in CMIP5, Isaac Held wrote a paper showing that in the GFTL model, at least, it was the trend was downward for Sahel rainfall.
I know for sure that was the case in CMIP3. I'm not sure about CMIP5.
Okay, maybe I'm thinking of CMIP3. Yeah.
But CMIP3 for sure, it's maybe I can just show you briefly. Where did it go?
Anyway, I don't, it's okay. It's okay, Ali, because I think if the results keep jumping up and down, depending on which CMIP you look at, then it's not a robust result, right? So
Well, no, the thing is actually, are they jumping up and down or not? It seems, my sense would be that in CMIP 5, they actually tend to go up
I
more
see.
than down.
Okay, all right. So
Whereas
it's not-
certainly in CMIP 3, there was this big, uncertainty because the GFTL model was doing one thing and the MIROC model was doing the opposite.
something else, yeah. So, but anyways, well,
And
now
then-
it seems like the first PCA, the first mode is, which is just everything is warming, is dominant, and the difference mode is not dominant. Okay, that's a
Yeah,
nice,
but that goes back to what you were saying. In fact, Alexei's question.
Yeah.
That's where my difficulty is now, because I do this in terms of if I standardize everything. But is that once I standardize everything, then I see that the sum, so the warming, takes over in the 21st century.
Mhm.
But is that really the right way, or is should there be a different way that we consider the magnitude of these two things, and how do we compare the magnitude of the warming trend compared to this difference?
Mhm.
Okay.
So
Because
I
in
have
the
a question
just
from Rainer.
because in the observations what we see is variation.
Yeah. I have a different question, if I may, Rainer. Yeah,
Yes,
this-
a very short one. We also have, okay, let me first take the one from Musa Saleh, and then it's you again, Balaji. Musa asked, what are the dynamics of large-scale phenomena like ENSO on Sahel drought?
Yeah.
Yes, that's a very broad question.
Hi, Musa. Yes. So the idea is this idea of what does the warming of the oceans do? In the most generalized way to look at it is what is the effect of warming oceans? And so, in general terms, if it's ENSO or the Indian Ocean, the warming of these oceans produces a warming aloft that increases the vertical stability, and so by that way, it reduces deep convection and precipitation. And so, the case has been made generalized. If you look at the area of tropical land under droughts during El Nino, you see that increases. And so, it's typically an El Nino or warm ENSO event translates into droughts over the northern hemisphere monsoon regions. So West Africa, India. Yeah.
Okay.
We can maybe discuss this next time I'm at AgriMet or somewhere near there.
Okay, then Balaji.
Yeah, this is a completely different question. So in one of your early slides, you mentioned that how Sahel rainfall is a global problem with a big climate change component, but people have been trying for decades to make it local. And you said that the Great Green Wall is also trying to make it local. So is there something we should be? Is the Great Green Wall? Maybe this is a controversial question, but is the Great Green Wall trying to basically say Africa is your problem, it's nothing to do with us, or is it? So where is the role of the big emitters of carbon in Sahel rainfall?
Can you maybe explain what the Great Green Wall is?
Yeah, I think Ali should do it rather than me.
Yeah,
The Great Green Wall is this idea that, the initial conception was this idea that if you planted trees at the border of the Sahara deserts, then you could stop the encroachment of the desert.
Okay.
In very simplified terms, but I think it's moved away from there. But yeah, I think I understand you, Balaji. It's my concern too that, you talk about climate change globally, you talk about other things, and you come and talk about climate change in the Sahel or Africa and you're talking about the Great Green Wall, whereas you should be talking about energy and transition to no carbon energy, or, that's really where the development is. There's no development without energy. There's little energy, little emissions from these countries right now because there's little energy. And so, yeah.
Okay.
I don't know, what can we do to shift the discourse on what climate change means for the Sahel and for a good chunk of Africa.
Yeah, but thank you for raising the question. I thought that you raised a very important question on your first or second slide. Thank you.
Okay.
Yeah,
so,
Vincent, I agree. I don't know if Vincent wants to say something more about the Great Green Wall. I agree with the note he put in the chat, that it was a very simplistic idea, this one of planting trees. I think based on also on the experience that I showed you briefly of what it meant to adapt and to respond to drought. The great.
we don't really hear you. Okay, we have a bad connection to Vincent.
Oh no, it's simply because I've locked up my computer. So my mic was basically that. No, it's things are moving away from simply planting trees. But what is still lacking, it seems, is a real sort of research insight on really what to do. At the time of the first phase of the Great Green Wall, I mean, there was absolutely no consideration of underground water, for example. And so talking to hydrologists, I mean, they were telling me, you know, we could have told them it would not work. No? So maybe the question to you, Alexandra, is it still realistic to think of a Great Green Wall sort of initiative if in the end, I mean, it all depends on the climate around. No? So you may want to try things that are not going to work simply because the future climate are not conducive to do anything.
Yeah, definitely. You should take into consideration what sense we may have for how climate could change. Yeah.
But to some extent, the what you showed was the ditches being done locally. That is to some extent also geoengineering and part of. I mean, it's not planting trees; it's keeping water, right?
Yeah.
Or
yeah.
like creating ponds instead of green walls. That might be.
Yeah. But it's all a way to regreen in the sense of, capturing the water, harvesting the water, and so that allows for vegetation to grow then